Welcome and thank you for joining us. My name is Carmina and I'm your moderator for today's event. We have about 45 minutes of great content prepared for you with 10 minutes for questions at the end. Now on to the presentation. Welcome, Hee-Soo. The floor is now yours.
Thank you. Welcome everyone, and thank you for joining the Engineering Education webinar series. My name is Hee-Soo Lee, and I'm the product owner for SerDes and DDR products at Keysight DES division. Let me start the presentation with today's agenda. The first is a quick refresher on the Ethernet Standard and PAM-4 signaling. Then we will discuss the basics of transmitter and receiver modeling with IBIS-AMI and the interconnect or channel modeling techniques. Finally, we'll touch on 56G PAM4 electrical analysis and measurement with an example. Then we'll go for the summary. Okay, let's get started. If you are new to Ethernet standards, maybe the first hurdle you will encounter is to understand many names of protocols. I had the same challenge. The protocol name typically includes the protocol characteristics, such as data rate and transmission media. One example is 400GBaud-CR8, which stands for 8-lane protocol that can achieve 400 gig total data rate through 8 lanes of copper cable. Here is some of examples of protocol names and options. Also, using Roman numerals, the data rate for electrical interface standards can be understood. X-AOE means simply 10 gigabit per second, since X equals to number 10. For two numerals, such as CD-AOE, it becomes 400 gig, since a D minus C equal to 400. The next slide shows IEEE 802.3 standard annexes. 802.3bs provides the physical layer specifications which support 200 and 400 gig over optical links, and there are annexes for C2M, which stands for chip-to module, and C2C, which stands for chip-to-chip AOE. Similarly, 802.3 CD provides the physical layer specifications which support 50, 100, and 200 gig over copper and optical links. These standards are comprised 1x, 2x, 4x, and 8x 56 gig PAM4 lanes respectively, with a Nyquist frequency at 13.28125 gigahertz. This slide is just an informative slide that shows a typical Ethernet implementation for an Ethernet switch using 400 gig base-FR8 optical link and a backplane. Although retimers are used in this example, depending on a design, sometimes no retimers are used. As you can see, PAM4 signaling is used extensively everywhere in this example. All right, now let's take a look on PAM4 signaling, its characteristics, advantages, and disadvantages. We compare NRZ, which is non-return to zero, or PAM2, against PAM4 here from waveform and eye diagram perspective. PAM4 packs 2 bits per symbol, so that the bandwidth requirement is a half of NRZ. This means the throughput will be 2 times more of NRZ for the same baud rate. An example is 28 gigabytes for 56 gigabit per second for PAM4 compared to 56 gigabytes for NRZ. This is the primary benefit of PAM4 since it can double up the speed using the same channel. As seen from the waveform plots in this slide, PAM4 has 4 levels, whereas NRZ has only 2 levels, low and high. There are several naming conventions for the levels, such as -3, -1, 1, and 3, or 0, 1, 2, 3. Since the signal level for PAM4 is 1/3 of NRZ, the signal-to-noise ratio gets lower, around 9.5 dB. In other words, the system is more susceptible to the amplitude noise. In addition to it, the transmitter and receiver designs gets more complex, so that the cost of designs gets also higher. As we discussed in the previous slide, PAM4 helps the bandwidth requirement. If we look at the Nyquist frequency between NRZ and PAM4, as seen in this spectral density plot, we can clearly see the advantage of PAM4. The Nyquist frequency of 53.125 gigabit per second NRZ system is 26.5625 gigahertz. PAM4 requires a half of it, so that PAM4 system allows designer to develop products to fit cost structure of available channel technologies. This is a busy slide. Therefore, I don't plan to go through all the details here, but the main key takeaway from the slide is that there are many Ethernet standards, including electrical and optical, have already adopted PAM4 as the signaling technology. All right, now let's take a look on Ethernet application space that includes the transmitter and receiver and interconnects. The picture shows an example of Ethernet application space based on PCB to PCB with a backplane. The data is transmitted from the transmitter through BGA balls, PCB vias, PCB traces, backplane connectors, vias, traces, and the other line card, similar way back to the receiver. It's a long path where there are lots of signal integrity issues coming in. Design engineers need to model all of these to perform a signal integrity analysis. Then how do we model the transmitter and receivers? At 56 gig data rates, the SerDes equalization and clock data recovery becomes critical to open the eye. On the TX side, usually the SerDes has FFP. On the receiver side, usually you have CTLE followed by DFE and also CDR. In other words, the conventional IBIS models are inadequate for the applications. The AMI algorithmic modeling interface, which is extension to IBIS, addresses this issue by offering portability, IP protection with DLL or shared objects, interoperability, and super fast simulation speeds. IBIS-AMI became a standard from IBIS 5.0, aimed at high-speed SerDes, departing from the traditional SPICE-like IBIS flow. Now let's take a look on the details of IBIS-AMI. The SerDes system can be broken into 2 parts, analog and algorithmic for both ends. IBIS-AMI flow always calculates the impulse response of channel combined with TX and RX's analog portions. This is done through the process called AMI init. Based on the choice of simulation modes, such as bit-by-bit or statistical, and the existence of a AMI gateway function, there are several different calculation processes, but mainly through either convolution process or the stochastic properties of conceptually infinite bit sequence, where in fact there is no bit pattern per se. The algorithmic parts such as FFE, CTLE, DFE, and CDR comes with a DLL or a shared object which is called by the standard IBIS model. Because of the simplicity, speed, IP protection, and mix and match of vendors, AMI has been the main platform that brings the SerDes model and EDA tools together in the industry and has been widely adopted by all SerDes and system vendors. Most of SerDes chip vendors provide accurate PAM4 IBIS-AMI models for their SerDes chips. In this slide, I would like to share typical accuracy level of IBIS-AMI models you can expect with two case studies, one for NRZ and the other PAM4. The NRZ case, which is the picture to the left, shows good agreement between the measured and simulated data. The difference between the two is very small and negligible. For PAM4 case, we generated TX waveform with FFE in ADS. Then the waveform was downloaded to AWG, arbitrary waveform generator, to create a real waveform for the test. The channel data, which was QSFP28 3-meter cable, was measured and put it back to ADS to simulate the receiver performance. The comparison between the simulated and measured with a DCA scope shows very, very good agreement in general. This gives us an idea of typical accuracy level of IBIS-AMI models. Okay, now let's move on to interconnects or channels. As illustrated in this picture, the data is transmitted from a transmitter to a receiver through various channel components such as balls, vias, traces, connectors, so on and so forth. The question is, how clean the received signal is after going through this complicated channel that may come with signal integrity impairments, and also, can we open the eye after? In order to predict the system performance like this, we really need accurate channel models. The channel impairments that cause signal integrity issues include ISI, inter-symbol interference, reflections, crosstalk, intra-pair skews, and so on and so on. Typical channel modeling process for 400 gig Ethernet involves defining board geometries such as vias and anti-paths, modeling 3D connectors, and modeling host and compliance boards. One way of doing the modeling is to use measured data, but this is time-consuming and pretty expensive process, although it is called as golden standard. Definitely, frequency domain models are preferred due to high frequency characteristics such as frequency dispersion and skin effects. As shown in the table, there are several ways of channel modeling, but they are all come with pros and cons in terms of speed, accuracy, and capacity. Another practical but very accurate approach is so-called mixed domain approach. As the name stands for, this approach mixes full wave EM and quasi-static sorters for transitions and traces respectively. In ADS, we use FEM for the transition and CILD or VR Designer for traces. This approach is very accurate and effective as long as the length of the trace is multiple wavelength long with good grounding and sufficient spacing between traces. I believe this is typically the case for most of high-speed SerDes designs. The case shown here is for 3-inch single-ended strip line that shows an excellent agreement between the measured and simulate it, including TDR data. We just saw the single-ended case. What about differential pair? Yes, definitely. This approach also shows very good agreement up to 40 gigahertz for the differential case. Look at how the SERPENTINE 6-inch long line was modeled. It was simply modeled as a straight single transmission line, but it still shows very good agreement. The other interesting topic is on voids and slots. As we all know, due to some layout constraints, voids and slots are sometimes unavoidable. How bad? The voids to the channel characteristics. This test case shows the voids under a differential pair. Well, the size of the voids were swept. When we look at STD and SCC in this plot, the impact isn't surprisingly bad. Yeah, it still varies, but not too bad as we might expect. However, this doesn't mean that it is perfectly okay to have voids, all right? Actually, the real problem comes when we look at the mode conversions, which are SDC and SCD. Although the absolute number is still pretty low, less than 50 dB in this example, but they fluctuate a lot due to disturbance on the ground return path. SCC TDR clearly shows it within this plot. To illustrate it, I added some electric field plot data in the slide. With a bigger size voids, we can easily notice larger disturbance to the electric field compared to the one of small void size. What about slots? Since the common signal is mostly affected by the slot, we can easily notice a big variation to SCC than STD. Compared to the voice case, this is quite significant. For the mode conversion, we can see the value is higher than voice case, and we can also notice an abrupt change on SCC TDR impedance. Seen from this data, the slots are more dangerous than voids from the signal integrity perspective. In this slide, I put some extra information on the conduction current field plots for voids and slots. You can see that the conduction currents on the ground plane are much spread over due to the voids and slots. This could potentially cause some EMI problems of the boards. All right, now in this section, let's take a look on a clear example for 56 gig PAM4 design. For 200 and 400 gig Ethernet, there are two electrical interface normative compliances. Channel operating margin, also known as COM, is the one, and the other is IMASC compliances. COM is the normative channel compliance for 200 gig AOE-8, 200 gig AOE-4, 400 gig AOE-16, and 400 gig AOE-8. It is used for electrical C2C AOE, direct attachment copper and backplanes. The COM calculation is basically based on MATLAB script. For IMASC, however, it is used for C2M AOE based on ANNEX 120E, and it really requires host compliance board. For COM calculation, it requires a COM configuration file. I don't expect you to read this configuration file. It's because it's too small and very busy slides. but I want you to have an idea how the configuration file will look like. Under operation control, there is COM pass threshold, which is the reference figure of merit for COM calculation. One good news is that starting from ADS 2019 Update 1, ADS started to support COM flow in ADS environments. In this example, the channel passes COM specification since the values for two given scenarios are both over 3 dB, so that it passes the given A specification. And once again, since COM calculation uses MATLAB script for the calculation, ADS also uses same MATLAB script to calculate the COM values. IMAS compliance specified in ANNEX 120E, the actual test setup is from TP0 to TP1A with a scope as shown in the picture. The scope requirements are first, adding a fourth order Bessel-Thomson low-pass filter, and second, applying only selectable continuous time linear equalizer, which is CTLE. So the question is, how do we model the instrumentation, including the filter and signal equalizer, consistent with the standards? And how do we correlate the simulation results with the actual measurement data? Let's use an example below to illustrate the process. The board used here is a rear board from IBIS-AMI, which is a subdivision from Keysight, and all channels here are full wave EM modeled. The transmitter and receivers are also modeled with IBIS-AMI. The setup is for C2C, which is from TP0 to TP5, also called as a ball-to-ball configuration. Using IDIP probe in ADS, we can pick up any I data at any location of the channel. From the results shown in the slide, notice that the receiver IBIS-AMI model comes with DFE enabled. If we cannot turn off this DFE, it may mean that we cannot use the receiver model for IMASC compliance testing since it says only with the CTLE. Then how can we handle this? One of the ways of solving this problem is to use generic IBIS-AMI model from ADS instead of using a vendor-provided IBIS-AMI model for the receiver. This approach is what we called mix and match approach. It's because we are using the TX IBIS-AMI from a vendor provided IBIS-AMI model, and for the receiver, we are using the generic model coming from ADS. The test setup here, C2M, is from TP0 to TP1A, which is called ball to SMA configuration. The receiver represents the scope specified in the specification. With 3 dB of CTLE applied, we can see that the eye can be open compared to the closed eye from the channel data from one of the eye diagram data in this slide. What about the eye mask with the different values of CTLE? In this slide, we tried 6 different CTLE values to see the performance of eye against the other different value of CTLE. We can see the eye can be opened by applying CTLE for all 6 cases, but above 3 dB CTLE value, we now notice that I is basically over equalized. By the way, starting from ADS 2020, you can enjoy new CTLE visualizer feature that allow you to see the frequency response of CTLE as shown in this picture and select a given industry standard presets such as CEI 56GB, 802.3BS or CD, and PCIe, USB, and MIPI, and so on and so forth. Although the use of generic RX gave us a good solution, but still the fourth order Bessel-Thomson low-pass filter is missing against the specification. We can resolve this issue by sending the simulated waveform from ADS directly to DCA scope by using the special probe called FlexDCA probe, developed for connecting simulation and measurement domains together. FlexDCA probe collects ADS waveforms and invokes FlexDCA automatically and send the waveform data directly to FlexDCA locally or remotely to populate the requested slots with ADS waveform data. Here's the final results shown from FlexDCA. The results are pretty much the same as we've seen from ADS environment. However, by using the math function from FlexDCA, like shown in the upper right corner of this slide, you can put fourth order Bessel-Thomson low-pass filter along with the CTLE that can be directly applied to simulated waveforms from ADS to complete the IMASC compliance test. By using this capability, additionally, you can do complete jitter analysis in FlexDCA environment and do additional compliance testing to the simulated waveforms by using these capabilities.
All right, now let me switch it to a quick demo. Here is a schematic, the one we discussed so far during my presentation. This schematic includes a transmitter and receivers that were represented by IBIS-AMI model, and also this includes package data along with host and compliance board channel data. By using conventional iProbe, you can pick up any of a waveform as well as IE data from any locations of the channel, but at the same time you can use a specially designed FlexDCA probe. FlexDCA probe, if you double click it, you can open up the window where you can set up the settings for FlexDCA probe. It starts with a number of channels. Right now, the number of channels are set to 3 channels, but you can expand it to a number of channels. Number of channels are scalable. If you go and then set up the port type to either a single-ended or differential, and when you click apply, then it makes the more pins automatically to be connected to any of channels in the design. But since we are going to only use 3 channels to pick up the data, one from right after the transmitter and right after the channel, and basically the last one will be the one after the receiver that comes with a CTLE equalization settings. So let me go back to this FlexDCA probe. You can send the data directly the FlexDCA on this machine. We call a local, right? But also you can send the data to any FlexDCA installed over a network or any hardware that is connected to the network, you'll be able to send the data to those software as well as the other hardware, right? This is done through a disconnection setup, right? Once you set that up, I can go back to the channel, then I can see the first TX data going into slot number 5 and channel data going into a slot number 6, and then receiver data slot number 7. So I can imagine when I open up the FlexDCA, what channels I need to look into it. Okay. Once you are satisfied with the setup, basically you can go and then run simulation by clicking this simulate button. Once the simulation starts, ADS will run through entire design with a channel sim to get all the necessary data, and once the simulation is done, we'll be starting a FlexDCA automatically. So let's just wait a bit, and now we see that pop-up window of FlexDCA where ADS will be sending the data directly to all of those slots in FlexDCA. So let's just wait a bit. Once all the simulated waveforms are populated in FlexDCA, then we will be able to see all the channel data coming in to this FlexDCA. From here, as we discussed, one thing what we could do is going into the signals where we can see slot number 5 data, slot number 6 data, slot number 7 data. But our interest at this point in time is more like D6A, which is the differential signal coming into slot number 6, which is the channel data, right? By using special function in FlexDCA, which is called math, what we could do, we can bring this up and switch it to signal processing, and we can put a 4th order Bessel low pass filter, and we can set up the other cutoff frequency here like 33 gigahertz, and also we can use a CTLE function embedded into FlexDCA. So by dropping in and making the connection between the two, we can make a entire setup for a C2MI compliance testing, as we discussed. By clicking CTLE, we can see all the preset, but in this case, we're going to use IEEE 802.3 BS-CD-AOI 3dB CTLE setting. So let's pick that up, and we're going to input the channel data, which is basically D6A, as the input to this filter. And we're going to look at F2, which is the output data after going through 4th order low pass filter and CTLE settings. By putting the other different color to F2, we can go back to the signals and start to see the F2, which is the output data along with a 3dB CTLE applied. Okay, in order to make the other visibility a little bit better, let me close other signals and only enable the CTLE output results. Okay, so now we can see this is the results. 2 ADS simulated waveform from the channel by applying the other 4th order Bessel-Thomson low pass filter and 3dB CTLE as specified in the specification. If we want to change the other CTLE setting, we can go back to this window and choose the other different CTLE. as soon as you pick up a different CTLE values, you will be able to see the result changing right away. But this is too much, overly equalized. So let's go back to 3dB setting. Then we'll go back to the one as we saw a minute ago, right? By using the FlexDCA, not only being able to do the math functions, but also you can enjoy all pre-configured measurement capability in FlexDCA. For example, you can go with a PAM4 related measurements where you can do the TDQ or transition time and linearity and a lot of different things you can apply. So for example, if I like to calculate the linearity, then just go and then click. Then you can see the linearity values coming with it. And also if you like to go and then do some other things such as a transition time, then you can calculate those transition time right away. But not only being able to do the very good and customized a PAM4 related measurements, what you could do is switching to jitter mode. Then you will be able to calculate all the jitters, jitter related values right away. This makes the user's job very, very easy. But top of it, you'll be able to go and then run a compliance test. Here in this case, I installed the 802.3 BSCD test application with the data coming from ADS, which is pretty much simulated waveform. You will be able to do this type of data compliance testing as well. All right, so this is all of my demo, and let me switch to the presentation slide and complete my presentation with a summary.
All right, we have discussed various different topics so far, and here is a summary of topics we discussed. First, we reviewed fundamentals of 400 gig PAM4 signaling and electrical interfaces, and then we discussed the basics of IBIS-AMI models and the best practices for high-speed channel design. Then finally, we demonstrated how to apply simulation techniques to examine the constraints for 400 gig designs against a given specifications. Thank you so much for your time and hope it was valuable sessions for you. Thank you.
Now it's time for the question and answer session. Okay, Hee-Soo, here is your first question. This one comes from Tony. The mixed domain approach for EM analysis means you have to separate vias and traces into two parts, the via and transition and the pure transmission line. How do you choose where to place the separation?
This is an excellent question. This is currently somewhat a manual process and probably may require some experience and knowledge. Based on my experience is to choose the merging points between the trace or transmission line and the transition, such as vias, where pretty much transmission modes might be settled down completely. If this is too close to the transition, then we may not be able to capture the transition behavior properly. However, if it is too far, the simulation time may get too long since the line length gets longer. Therefore, that is a more like guidelines where we choose right location for the division. But I can tell you with several trials and practices, it becomes quite easy and straightforward process. And this is what I have used, my kind of approach to the examples I used in the slide or this presentation.
Okay, great. Thanks, Hee-Soo. Here's your next question from Peter. You mentioned most of SerDes chip vendors provide accurate IBIS-AMI models. However, there are cases where I can't find IBIS-AMI models for the chips. Then how do you model and analyze the design?
That's a good one, but pretty hard question. A couple of options that I can think of at this point in time. The first one will be is to use a generic IBIS-AMI model that comes from ADS, such as PAM4, PCI Gen 3, Gen 4, so on and so on. But this is only good for a testing algorithmic parts, but will be a pretty limited in terms of analog chips behavior. So that's one of the downside. But this is first option I can think of, and the second option is to use the COM calculations as we talked about during the presentation.
Thanks, and here's your next question. This one comes from Twin. Finally, it's great to hear that ADS supports COM. What COM versions does ADS support? Does ADS also offer the configuration files? Is MATLAB required?
Okay, multiple kind of answers. First, starting with the what version of the COM we support. It's basically we support the 1.54 and 1.65 and 2.28 and finally 2.6. So these are versions of a MATLAB COM calculation in ADS environments. In terms of a configuration files, yeah, we do support the most of configuration files you can find from the IEEE webpage. In terms of a MATLAB license, you don't really need it to run COM calculation in ADS if you choose to run it with the runtime. However, if you really want to run the COM calculation with that M script file directly, then yes, definitely you need to have a full MATLAB license on the same computer where you run the COM calculation.
Great, thanks. Here's a question from Marcus. Why only 8 channels for Flex DCA probe?
This is actually due to DCA scope hardware configuration. The rear DCA scope only supports the 8 channels because it's a measurement system or instrument, and that is exactly why Flex DCA probe limits number of channels for ADS waveform to be sent to max 8 channels.
Great, and here's a question from Chevron. Is it compulsory to validate COM for PAM4?
That is not always the case. We talked about the IBIS-AMI and COM. These are interestingly a little bit 2 different flow. And some cases, as one of the questions came out during the Q&A session, if you don't have any of IBIS-AMI model, then it's going to be very, very difficult to follow IBIS-AMI simulation flow. That's where COM can be another option for users to test or validate their channels because it doesn't really require IBIS-AMI model. But if you go back to the 802.3 DS compliance, as we talked about, COM is one of the other way of validating the channel or system, and also IBIS-AMI can be used. But again, COM is one of the other options you can actually go for. Make sure the design meets the specification. One with definitely a COM, and the other IMASC compliance.
Great, thanks. And here's a question from Kongman. I saw the results on Flex DCA still updating. Is the data from ADS still running real time for Flex DCA to process?
Yeah, that's a really excellent question. ADS is more like a static simulator. If you go to the other simulators that like Ptolemy or System View, then it is a data flow where you just keep running the simulation over and over. However, ADS is not like that. Therefore, you make a chunk of a number of bits simulated and then send it to FlexDCA. Then in FlexDCA environments, that number of bits coming in from ADS will be repeated, which is coming through the the FlexCCA capability. That is why it is basically showing the waveform data keep updating, because it is running the same a number of the bits simulated in ADS environment and repeating.
Great, thanks. And here's a question from George. For voids and slots, did you parameterize the design and simulate them once? And what tool did you use for it?
The answer, yes, I did parameterize the design. Otherwise, it's too much work. And then simulate it once by running the more like a SWIP A simulation in the tool. For this example, I used a tool called EM Pro, which is a full wave 3D EM solver. That was the one I used in this application.
Great, thank you. And here's another question for you from Chevron. Will IBIS-AMI for NRZ and PAM4, will it be in a different format?
IBIS-AMI is same for NRZ and PAM4 because it's just following the specification given by IBIS-org. But in terms of the modulation format you need to choose, yeah, definitely there is a different setting for it. Okay.
Great, thank you. And then here's a question from Christy. Does FlexCCA probe require a license?
The FlexCCA probe, what you sell in ADS, it doesn't require any of a license. That is part of a simulator called Channel Sim in ADS. However, you may need a license for FlexCCA itself. If you really want to do PAM4 a specific measurements. For NRZ applications, then you don't need to have a license. But again, in order to do the PAM4 specific, then yeah, definitely you need to have a advanced R&D package for FlexCCA.
Great, thanks so much, Hee-Soo.
Yeah, first of all, I'd really like to thank everyone to come and join. And if you happen to have more questions, could be related to the this topic, or could be any service related questions, then please don't hesitate to contact me. But again, thank you very much for your time today for this webinar.
Great, thanks so much, Hee-Soo. Thanks again for attending today's webinar brought to you by Keysight Technologies. Join us next month for a continuation of our engineering education webinar series, and enjoy your day.